trees. But if you didn't graduate from kindergarten, here's a quick crash course. A data structure is just a way to organize data in a computer so you can do CRUD to it efficiently. Create, read, update, and delete it. An array is like a row of numbered cubbies. A linked list is like a treasure map of clues. A hash table is like a locker with your name on it. A stack is like a stack of books. A queue is like a line of kids at the cafeteria. A graph is a spider web. And a tree is, well, like a tree. Programming is all about solving problems. I've got 99 problems, but a data structure ain't one. But for some programmers, data structures do become a problem. And in today's video, we'll look at a few unusual situations where these simple data structures were not good enough or smart enough to get the job done. Let's start by talking about the B tree, not to be confused with a binary tree. One of the most exhilarating things that ever happened in my life was the first time I implemented a binary search tree, which prevented my algorithm's time complexity from going burr, turning O of n squared into a much faster O of log n. But binary search trees have one problem. Each node in the tree can only have 2 children, which means the depth of the tree grows rapidly, and doesn't scale very well for things like modern hard drives with massive amounts of data to search through. To address this problem, a long time ago, programmers at Boeing developed the self-balancing tree, or B tree, although nowadays you'll mostly find B+ trees in file systems and databases. At a high level, what makes them special is that each node can have multiple children of sorted keys. These are called internal nodes, and they work like signposts that point to leaf nodes that hold the actual data, or pointers to data. So it works kind of like a binary tree, but greatly reduces the disk I/O operations by cutting down the height of the tree. Pretty cool, but there are many other types of trees in nature and in computers, like the radix tree. Like, there are billions of IP addresses in the world, but have you ever wondered how computers route between them so efficiently to make the internet work? A radix tree is special because nodes with only one child are merged with their parent, and that makes them highly efficient when finding values with a shared prefix, like an IP address. For example, if I made a tree to find words that start with C, our tree might look like this, but in a radix tree we can reduce the depth by merging the last child. That's ideal when you have many shared prefixes, but doesn't work so well with big complex strings, like all the vibe-coded slop you're trying to debug in your IDE right now. A rope is yet another type of tree that breaks down strings into manageable chunks. Instead of one continuous strand, you cut it into many smaller manageable segments. Then you tie these segments together using smaller knots that also tell you how long each segment they represent is. This allows tools like text editors to more efficiently modify large documents. But in some cases, figuring out what not to search is more important, and that's where Bloom filters come in. It's a probabilistic data structure that can tell you if an item is definitely not in a set or maybe is in a set. It works by using multiple hash functions to set and check bits in a fixed-sized array, allowing fast membership tests with possible false positives but no false negatives. It's like a bouncer at a club who always knows exactly who to kick out. One of the weirdest things in nature, though, is the cuckoo bird, a bird that sneaks into another bird's nest and replaces its eggs with its own, tricking the host to incubate and care for the cuckoo chick. This behavior not only inspired the term cuckold, but also cuckoo hashing in programming. According to my wife's boyfriend, it's a collision resolution technique where each key in a hash table has 2 or more possible positions, and if one spot is taken, the existing key is kicked out like a cuckoo and reinserted in an alternate location. The end result is constant time worst case complexity for lookups, which is as fast as you can possibly go when it comes to algorithms. But if you want to optimize your own code with these weird data structures, you need to know about CodeRabbit, the sponsor of today's video. They just released a new VS Code extension that gives you advanced code reviews right in your editor, so you can catch the majority of bugs before you even submit a pull request. Unlike other tools, the extension understands the context of your entire codebase, allowing it to catch more bugs, like all the AI slop your favorite code gen tool left behind. It gives you line-by-line comments on all issues so you can see it reasoning, then it offers simple one-click fixes to help you clean things up quickly. CodeRabbit is free to use in the IDE and works seamlessly with VS Code as well as forks like Cursor and Windsurf. Download the extension using the link below to try it out. Thanks for watching.
Okay, let me get the new link. Okay, the link is in the chat. Also, I don't know if you guys are interested, but yeah, B trees are pretty important, especially for file systems. So like file systems are used for your operating systems like Linux, Windows, and also for hard drives, which are pretty important. And so the link is in the chat. You guys can open it and we'll continue with Connect 4, I think we left off at, let me share my screen. So we left off at Play Human Burst, MCTS, Monte Carlo Tree Search. This is basically the main game loop. So we're running simulations using the Monte Carlo tree search. So we'll continue doing that. So let's start with, oh no, Adam, can you share your screen? And we'll continue off whenever you're ready. And then we'll finish that today, and then we'll start off with Q learning after.
How do I share screen?
Oh, let me enable your share settings. Okay, I think it's good now. Zoom changed their layout. Can you try sharing now? I think it should work. Thank you. Can you go up a bit? Let me see what function you're working with here. So I think it's your the code should be below this, but there's no code below this. Let me share you the GitHub link. And you can try and getting it from here. I pasted it in the chat. I think you can just copy the whole file and then paste it in your Replit. And I would say just delete everything in. Okay, sounds good. And then when you're ready, Adam, share your screen again. Now, Adam, we can just continue on. You can just share your Replit again, and we'll start. Okay. Go all the way down to, yeah, I'm not sure what line it is, but down, down, down. It should be after the classes. After this, down, down, down. Because it's all part of the same class, so you have to go a bit more down. And then the next function, this one, right there. Up, go up. So you see, yeah, that one. 2252, line 2252. Yeah, delete that, and then we'll get started. Yep. Now you can go ahead and read what we were trying to implement before. Delete the arrays not implemented as well. Yep. So then this is the main game tree. So basically you're going to print out the board. And if it's the AI's turn, we're creating this instance of the Monte Carlo tree search node. And basically using this and using the class's functions like simulate to simulate our Monte Carlo tree search. And after the simulation's done, we're applying the move with make move. And if it's the human's turn, we're basically just prompting the user. Make sense? Yeah. So continue on with where we started. Delete that raise not implemented error.
It was never there.
Oh, weird. Okay. Line 2252. That's where we're going. Yeah, right there. So if the current player is player one, then we're doing Monte Carlo tree search. So this is basically the AI. So we're doing Monte Carlo tree search simulate function. We're doing simulations equals simulations. And the simulations variable is defined at the top of the function. So our argument, where we set simulations to 60. And then we're making this board.makeMove using this move that the Monte Carlo tree search determines is the best possible move. Best move. Yep. And then we're inputting into this makeMove function of the board, Monte Carlo tree search. We're inputting the board and the player. Are we inputting the board though? If you hover on the make move, oh, actually, it wouldn't because your code is on Replit. So you're passing in move because make move, we're basically saying this player that we pass in will make this move. Move. Yep. Next line. Now we're done with this AI player. So we're doing else. Yep. And this would be us, the human player. Remember that else statement? You're missing something. No, else is fine. It's just you're missing the colon, right? Yep. And then we're doing fetching the legal moves, whatever you want to call it. In 1 second, let me copy the live share and give it to Kaden. Kaden, the live share link is in the chat. And yeah, Adam, you're going to want to call legal moves and set it to a variable. So go ahead. So legal moves is a function. How would you call a function? Yes. And then, so what is the legal moves a function of? Remember that legal moves is part of a board, right? So board is a class. The board class has a function named legal moves. So you would do board dot legal moves instead of legal moves of board. So delete the board. Yep, board dot legal moves. And you don't pass in anything. Yep. So now we want to set the output of this function to a variable. So how would you do that? We want to set it to like legal moves equals, right? Remember that you're calling the function, so you have to do it before the function, right? In the same line. Before board. Yeah, right there. Right? Do you understand this? That we're basically setting this legal moves variable to the output of the function. Do you understand that? You can just type it in the repl. And no worries, Kaden. But yeah, that's how you set a variable to be the output of a function. Now we want to set the move to none because we're trying to get the move from the player. So we first set it to none, enter, and we want to run this while loop while the move is not in the legal moves. Yep. And we want to so try and catch or accept. Does everyone know what a try except block is? Please ask any questions if you guys have any. Basically, you're trying to see you're in this try block, you're running something. If there's a error, we don't crash. We immediately go to accept value error if it is a value error. And then instead of crashing, we're telling the code to continue on and skip this iteration of the while loop. And yeah, try, and then inside the try, we're gonna ask the user for input. So we're calling move equals, go ahead, equals int of whatever the user input is. And the prompt should be, it's your turn and choose a column or choose a move. Does everyone understand why it's while move not in legal moves? I'll assume you guys do. Yep. Choose column. You're inputting legal moves. Except this would not work, right? Because the legal moves here would not be the variable. Because we want to call or print the variable. One thing here you're missing is the F. So F strings, basically you have to put it before that quotation mark in your input. Yep, right there. So this is called a F string. Oh no, you don't need that. Yeah, you don't need that. Yeah. So F before a quotation mark basically lets us do that curly bracket, and inside the curly bracket, if we put a variable, it'll make it a variable. So we're printing out all the legal moves. Yep, enter. Now we want to catch an exception. So delete, delete. Remember that try except block, so they should be on the same line. Oh, you need a tab. They should be on the same line. Yep, right there. Except, and our exception is the value error. Yep. And basically the value error would be like a string or something doesn't work out with the value. Yep. If it's a value error, we want to continue. If not, outside the while loop, we now have our move. So we want to make move. Continue uh, back again because we want to be in the line of while loop. You don't need else. Remember, because it's a while loop, you don't have an option for else. Yep. Go ahead. We want to call make move. And we're basically making the move for the player two, which is us, or the user. Move, comma, player two. And then enter, enter. you should be now on the same line as else. And we want to set the current player like that because we want to now switch the player every round or every move. Yep, set current to equal to player one if the current is player two, or you can do it the other way around, doesn't matter. And if not, then player two. Yep, two else, and then player one, player two. You need the else block. So at the end of the line, else player two. So how this works is this is an inline if statement. We're saying do current equals player one if the current player right now is player two. If not, then we're setting current equal player two. Does that make sense? Any questions? If not, that's good. You can stop sharing. And I'll show you guys. Let me share you my screen. Assuming you guys can see my screen. So you guys implemented the Monte Carlo tree search. If you guys want to run it, you just uncomment this line, which is just calling our game loop, which is play human versus Monte Carlo tree search. Actually, let me zoom in maybe. I think this is better for you guys. Anyways, play human versus Monte Carlo tree search. You can adjust the simulations. So by simulations, the more simulations you have, it's typically better, but it's pretty like it will run a lot, so I wouldn't recommend. So the more simulations you have, the better our AI will be. I set it really low. Usually you want like thousands, but we don't really need, we just need to show that it works right now. So let me now run it. Um, Done. And we can see that they already made their move. The Monte Carlo tree search placed the X in the middle. And we made our move, which is 0. And basically, this is the column 0, column 1, 2, 3, 4, 5, 6. And I placed my connect 4 inside column 0, and then Monte Carlo tree search, placed their X in column 0. And if we continue, they'll continue doing stuff. And this should basically be good. And it would be way better with more simulations. So let's do like 8,000. But you guys can play around with this. See what's good. Yeah. Actually, let me clear the screen. Okay. You guys can see how it's taking longer, right? This is because it's running 8,000 random simulations. And you guys can see how it impacts your computer. Let's actually set that lower to 500. 500. Here. Anyways, you can see how it took longer after 500 simulations. And basically, you guys can play around with this later. We'll continue on now with, why does this happen? Now we'll continue on with Q-learning. Let me show you guys class. So here's our Q-learning agent, or basically building this agent for our Connect 4. Now, about Q-Learning agent, it's basically going to be, how do I explain this? It's an agent instead of, you know how for Monte Carlo tree search, we're basically doing random simulations. It's all random. We're basically choosing a random column, playing it out, and keeping track of the score. For Q-Learning, it's basically we're building this AI agent, which will keep track of its own score and think for itself about what the better option would be. Now, a better way to explain, we'll just watch a quick video on Q-Learning and we'll implement it. Let me know if you guys can't hear it.
This is the mountain car problem. The car at the bottom of the hill is controlled by a reinforcement learning algorithm. The goal is to get the car to the top of the hill, but the caveat is that the car does not have enough energy to climb the hill by itself. It needs to roll back and forth to gain some momentum to eventually get to the flag that's in the top right corner. A successful case looks something like this. But how do we develop an algorithm to do the same thing? Before we can develop an algorithm, we need to understand the reinforcement learning framework. First, we need to introduce the agent. The agent is the algorithm, and to start the reinforcement learning process, the agent takes an action. This action is taken within an environment, which results in the mountain car moving back and forth on the hill. Then, the environment gives the agent a reward for the action and a new state. The overall pattern is each state corresponds to an action that is chosen by the agent. Then the environment gives the agent a reward for said action and produces the next state. In this case, we only reward the agent for reaching the flag in the top right corner. That's because if we were to reward the agent for, say, going right or going left at certain times, it'll exploit that in the algorithm. And so instead of actually reaching the flag in the top right corner, it'll instead really exploit going left or going right, and it'll never actually accomplish the task. And so a very fundamental rule of reinforcement learning is reward the agent for the end result. Otherwise, it'll just get stuck in the middle and it won't do what you want it to do. Now that we understand the reinforcement learning framework, we should collect some data to get an understanding of how the agent interacts with the environment. You can see how the data points move in a circle. This reflects the back and forth motion of the car as it attempts to climb the hill. This specific graph is called a state space, where the x-axis is the position of the car and the y-axis is the velocity of the car. Now we are going to parameterize this space using a concept called tiling. Tiling is making a grid that allows each square to be a Q value. I can place this grid wherever I'd like to make the problem solving easier, but for now, we'll just place the grid here. I do understand that I said the magic word that's Q value, so how about we go through a quick derivation to understand what's going on. In reinforcement learning, a sequence of state, actions, and rewards that end with the agent reaching the end goal is called an episode. We know that the number of states and actions is finite. This means that the rewards are also finite and can be written like this. The rewards are collected sequentially, and G is called the return. We can group the future rewards like this thanks to algebra, but we notice that the reward in the future is the same as the future return. So we need to predict the future return. This is the Q value that everyone talks about. The funny looking character in front of Q is called gamma. That allows us to determine how important future returns are in our calculation. Higher gamma values mean the Q value has more weight, while smaller gamma values means the Q value has less weight. Let's take the current Q value and subtract it from the next Q value. This generalization allows us to examine every case instead of looking at each case individually. Subtracting the current Q value from the next Q value gives us a gradient, or rate of change, for how well the agent is performing. To update our Q value, we take our current Q value plus our gradient, which is everything being multiplied by the alpha parameter. You can think of alpha as a parameter that decides how large the gradient should be. If we want our Q value to change in very large chunks, we would want alpha to be very large. Whereas if you want very small micro changes in our Q value, alpha should be very small. To turn this into Q learning, we change the next Q value with a maximum. This will force the algorithm to pick the largest Q value, which is corresponding to the best action. We incorporate the Q values by using the tiling method. Each of the squares you see on the screen gets assigned a Q value. Once we do that and allow the agent to learn over a long enough period of time, is how we get the solution to the mountain car problem. I do understand that people like compilation videos.
So if you have any questions, ask. But basically what it's talking about is for Q-learning, we have the board. We'll call this our state. And basically this AI agent or Q-learning agent basically runs a simulation. It gets a reward based off that, and then it updates the state. And it keeps on going. And this like simulation is called episodes. So if we, after like, I don't know, 1,000 episodes, then our state would have changed into some Q values. So of the Connect 4 board. So we're basically gonna use the Connect 4 board, which is like 6x7, and we're gonna set that as our state. We're gonna have each cell of the board equal to a Q value. We're gonna run the simulation using the AI agent. It's gonna get a reward based on how it did, if it won or not. And then after it's got that reward, it's gonna update the board using the Q value, like update the Q value. And through these episodes, like say 1,000 episode later, it's gonna have this new Q value state. And whichever is the highest or the maximum will be our best move possible. Let's begin now. Let me share my screen again and then show you guys what code we'll be working with. And you guys should ask as many questions as you can if you guys do not understand. So we're making this Q-learning agent class. So as I said, the state representation will be the board, which is 6x7 NumPy array. And here we have our init, which is our construct. We have our player, we have the alpha, the gamma, and the epsilon. And if you guys are wondering what these are, stays here. Epsilon is basically our learning rate. As the guy said, it's basically our multiplier. Discount factor, basically gonna be like our reward. Epsilon, exploration probability. So this is where we're making this decision of should we keep on going with what we chose last time, or should we explore some new possibility? And this is determined by some probability. Next, the Q table. Like I said, this is the state. It's basically gonna be a dictionary of representation of our board. Next, encode. This is a function of the Q-learning agent. We're basically going to encode the board into a hashable string. So we're making this self.q. GetQ, we're getting the Q vector for a state. Select action, we're going to select the action. Nothing much to be said there. Q-learning update rule. This is basically the equation that you talked about, or this is how we're going to update the Q value. Here you guys can see we're having the reward, the gamma, the Q function. Train self-play. This is where we're running this episodes. You guys can set it to whatever. I'm just going to set it to 5,000. And that should be good. And then for the game loop, here's our game loop. We're basically running the simulation using, human versus trained AI. Oh yeah, one thing to be said about this, we're training beforehand. And using this trained model as an opponent. And as you guys might know, this is how AI usually works. We're training the model and we're giving it out, exporting it for others to use. Okay. Albert, can you share your screen whenever you're ready? And the live share code is in the chat, so you can open it. And next will be Caden, so just get ready, Caden. Let me accept your. If you see on the bottom right, do continue as anonymous or sign in, up to you. Enter or yep. And I accepted it, so you should see it now. Yep. Go to template. Go up. You should go up to line. Let me see. $359. Oh yeah, right there. Go down a bit. Yep. Let's do encode. And encode, or basically making the initial state of the queue, which is going to be our dictionary or the state. Okay. You have to go open code. That's the solution. So go to code, week 6. Yep. Delete the arrays not implemented error. I think you need the extra space. Yep. Okay. So to encode, we basically convert the NumPy to a hashable string. So first we'll set it to, I don't know, board string, or set a variable named board string, board str. Uh, all in one word. Equals board.grid dot ravel. RAVEL. No G. So what this is doing, we're flattening the array. So first it was a 2D array. Now we're doing a 1D. Now this is a function. Yep. Now we'll initialize the empty list. So initialize the empty list. Call it like string parts. Yep, string parts. One word. Remember that variable should be one word. Equals empty list. You know how to do an empty list? So it's either a list function or square brackets. Yep. Enter. No, that's it. Uh, the closing square bracket, right? That's the list. Enter. Yep. Now for each of the board string or the flatted value, we want to do everything. So do like for, something, make a random name for cell in board, board str. And then we want to convert the value to an integer. So remember that for loop is a colon. Although on your keyboard, can you type insert or tap insert? Yeah. So do you know what that is? I think you tapped it. Okay. Basically, if you go up one cell, yep, and then type J. You see how it adds it? Now do backspace, type insert, and then J. This one basically replaces that letter, but yeah, that's what that does. Anyways, we'll convert it to integer, so do like integer value equals. Do you know how to convert cell to integer? I don't remember. Okay. Then let's make the variable first. So integer cell or integer value, int value or int cell equals int int, and int is a function. Is a function. Yep. And inside the function, we want to pass in cell. Inside the function, yep, pass in cell. So this is how you convert it into integer. We're basically calling the function cell, I mean int on cell. Now, after we get the integer, we want to now convert it back to a string. So str value or equals str is a function, and we pass in int int value. Next, after that, we want to add it to our collection. You see our empty list there? We want to add it to that. So do string parts. And how would you add something to a list? Do you know? What do we do? Not really. That wouldn't work. Append, right? So do string parts dot append. Yep. And input our string, which is string value or str value. Str value. Good job. Now enter. So we want to get out the for loop. So delete. We want to get outside the for loop. Yep. And then we want to return all our string parts list as a string. How do we join everything in string parts and output it as a string? Do you know? You used that function just now. What did you put instead of append? It was join. Yeah. Now before the dot, it should be empty, just quotation. We don't really want no space. Space means we're separating each value inside string parts with a string. We don't want that. We just want to concatenate it. Yep, join, and then we pass in string parts. That should be good. That's it. So you can stop sharing your screen. Next, Caden, if you can share your screen. And Charlie, you'll go next after him. So just get ready. Yeah. Down to we want to do get cube. So that's okay. That's a pretty. But it's 296 or something. Are you in the right one? Week six. Yeah. Go down. I think it was more down, I think. Down. Like, yeah, down. Should be after the Monte Carlo tree search class. So that's the way down. That's the board class. That's the Monte Carlo tree search right there. Q learning. And go to get Q. Right there. Yep. This is going to be a really easy function. You got lucky. But yeah, we're going to return the Q value for a given state. So it's basically a getter function. If you guys know that. If you guys don't, getter setters are pretty well-used functions in C or C++. But you guys don't need to know that. Go down to 402. You should delete the arrays not implemented there. Tab, or yeah, enter. Your code should be always after the docstring. Function docstring. Anyways, if the state is not a key, then we want to create it. So if state not in self.q. Yep. And remember that state is being passed inside the getQ function, so you don't need to define it. And we're setting the queue's state. Yep, self.q state. Yep, state equals numpy, which is np, zeros. And this basically sets a numpy array of zeros. And we're passing it columns, the number of columns we have. And enter, we want to return the Q state. Remember, should you return it there? Yes. Because if you do it there, then it will only execute if the state is not in self.q. And yeah, that's it. Thank you. Next, Charlie, if you can share your screen. And we'll go on with select action. Weird. Can you click the link again, maybe? Bottom right, continue as, yeah. And I accepted it, so you should be. Yep. Now go to the 3 lines. Okay. 3 lines, that's the solution, so 3 lines. Oh, I mean the bottom below the 3 lines. Code, week 6. Yep. And it should be line 3. Oh, it's right there. Q learning. Then you want to go to select action. Yep, right there. 408. Yep. And basically select action, we're basically selecting the action like the name says. Basically, you're going to choose a column for the current board with a probability of what we talked about, which is epsilon. Otherwise, we're going to pick a legal column with the biggest Q value. So first, get the list of legal columns using the board's function, which is legal moves. Remember that you want to set it, right? Set it to a variable. Choose a name, yeah. And next, we want to encode the board. So we already have this board's encode function, right? So you want to do board dot. Remember that this encode is not a function of the board, right? Or it's a function of this class, which is QLearningState. I mean QLearningAgent. To access a function of its own class, we want to do self dot encode. Yeah. And we pass in the board. And this encode returns returns a state. So you want to do state equals. And now we want to fetch its Q vector. So the Q value. And we already have that, right? We have a get Q function. So you want to do it again. Self dot, remember? It's a function of its own class. Yep. And we pass in the state. If you're always unsure of what goes in the function, you can always hover on it. But yeah. And this get Q returns a Q value or vector. So you want to set it to like Q or something. Q equals. Just do it lowercase q. Reason is always assume uppercase is basically a class. But yeah, next with a probability epsilon, you want to return a random legal move. So if random.random is less than self.epsilon, remember by seeing the notation, you should assume that epsilon is a variable of the class. So it should be defined inside the init function. And good job, yeah. It's not a function, it's a variable, so good job. Now, if it is that, remember you forgot a colon. And if it is that, then we want to return a random choice, random dot choice of the legal moves, or in this case, yeah, legal moves variable. Yep. Next, else. You don't really need the else, but you can, yeah, just delete the else. Now, this is the case where we want to exploit it. So you want to pick the highest Q among the legal moves. So do like best underscore Q equals the max of Q's C. So Q, and we're accessing the C, which is column. For, yeah, C, that's good. One thing here, inside the square bracket, it should be C. The four should be after the closing square bracket. Yeah, that's the notation. For C in legal moves. Yeah, so this is the notation. You always want to do what we're going to set it to for C in legal moves or for I in range of whatever. Next, we want to do best moves. So this will be C for C in legal moves. This should be a list. Inside the list, we do C for C in legal moves. If still in the same, yeah, if Q QC Q's bracket C is equal to best underscore Q. Remember, conditional is double equals. So you get the notation here. We're basically saying for each of the legal moves, we're checking if that legal move is basically the best Q, right? Next should be returning, right? Now, so we want to return choice of the best moves. Remember, choice is a function of random. Yeah, good job. So this is important, so I'll reiterate. You can stop sharing. So reiterating or fetching the legal moves or encoding the board or getting the Q value of the state that was returned by the encode or checking this epsilon because this is so whatever's inside of here means we're exploring. Whatever is not inside epsilon, we're exploiting. Exploiting means we're choosing the best Q value. And why are we filtering with legal moves? Is because if the whole column is full, we can't really even play there, so it doesn't even matter. Anyways, yeah, exploring, we're doing a random one. Exploiting, we're choosing the best one. So we're choosing the best using max, or basically finding the max of the legal moves. Now using this, we're finding the best move. So we're basically looping through this and saying, grab every Q value that is equal to this. So we might have the multiple Q or multiple columns that have the same Q value, right? So they might be equally good enough. And then we're basically just choosing a random one of the best choices. Let me know if you guys don't understand or if I'm confusing you too much. Next should be James, are you able to share your screen? Let me know. Okay, then we'll do Nicholas first and then we'll move on to James after. Nicholas, can you share your screen? Okay, thank you. Whenever you're ready. Thank you. And you should see it. So yeah, Connect 4 template. Go to update function. It should be below. Yep, it's that one. Basically, what you're trying to do, we're basically just updating the, the board. So you have the, what do you call it? The kind of equation to update the board right there. And as it says below in the comments, we're basically checking if the action is none, then we want to just return. If not, we want to encode the state and the next state. We want to retrieve the Q vectors. So basically, this is all doing getting the values ready for that equation right there. So if we step through this, we want to first check if the action is none. So first, let's just check if the action is none.
Where do I put it?
Right there.
Underneath
Enter.
here or?
Oh no, that's the docstring. So the docstring should always be at the top of the function. So go after that. You should see the raise not implemented there. Delete that
Do I
one,
delete
and then
it?
just yeah, and then start writing. So raise not implemented there. Well, raise error. It's basically as it says, raising an error. If the code runs into this, it will output in the terminal not implemented error and basically exit. But yeah, you want to delete that. Usually program is just leave that as we didn't implement this function yet. But yeah, first let's check if the action is none. You know how to, yeah, if action is none,
You know how to turn it off, like, because every time you move, it keeps following you.
I don't know if I wonder if I can separate from myself. Oh, let's just keep doing it. I'll find it out next time. Do if and then brackets and then action is none. You can just do is because it's Python. Remember checking is equals equals. Yeah. Colon, yep. And you want to return right away. Yep. Now we want to retrieve the Q vectors. You just want to return nothing. Let me check how this. See if this works. I think it should work now. Weird. Yep. Go ahead. We'll do to do number one now. Encode the current state. So do you know how to do that? Enter and delete. Yep. You want to be in the same line as if, and you want to encode it. Do you know how to encode it?
Mm.
Remember, it's a function of the Q-learning agent class. So you want to, it's its own class, right? So you want to do self.encode. You want to access your own function. You see it right there, encode, bracket, and you want to pass it in. If you hover on encode, you can see that you want to pass in a board. You want to pass in the current state, right? Do you know how to do that? Do you know how to do that?
No.
Okay. So basically, you want to do, so do board, input the board. Did it just keep on following me,
Yeah, it
even
does.
if I scroll up?
Yes.
What? Even if I like switch tabs like this? Does it show on your?
Wait, switch
Yeah.
tabs again. Yes.
Wow. Okay. Then I'll just leave this. But yeah, go ahead, state, go down. Okay. Maybe I have to go down. Okay, this is probably better. Do right here. So self.encode board.
Yeah, there's nothing. There's nothing that stops me from following you.
Hmm. Okay, let's just continue on. I'll just leave my screen like this. So do self.encode board, and this returns a state. So let's set it to state equals. So remember that the encode function returns the state. So when you want to set it, you want to do state equals self.encode. So you have to put it before you call the function. In the same line though. So right before self. Yeah, right there. So state equals self.encode board. Next, it says we want to encode the board and then the next state. So we do s state or state underscore next, since this is the next state. State underscore next equals self.encode next underscore board. Now, where is this board and next underscore board coming from? If you look at the function header for this update function, you'll see that it gets passed in. So right there, we see the board, we have the action, we have the reward, and the next board, and done. Okay, next line we want to do, no, we want to get the Q value. So Q equals underscore Q. I mean, lowercase q equals self.getQ. Remember, we're calling this getQ function from this class, and we're passing in the state. So this is using the current state, and we need the next state as well. Pass in the state. Like as an argument. So do self.getQ state. Because getQ is a function. Circular bracket. Circular. Like circle. Yeah. Yeah, that one. State. Next, you want to also do next Q or Q next, doesn't matter. Next Q equals self.getQ, and we pass in the state next. Right? And one thing about the next Q, if it is not done, then we want to pass or set next Q to be numpy zeros. So how do you do that? You have to go after the self.getQ state. One thing here, go back to the previous line, delete the if. You passed in state, not state next.
Statement.
Remember you set state underscore next in line 470? You want to use
Oh.
that, right? Yeah, that one. Good job. Now, after the circle bracket, yeah, if not done, else not done, not space done, no underscore. So this is a conditional. Else, we want to do np.zeros. ZEROS. And this is a function we pass in calls. COLS, all caps. It's a function, right? Function so circular bracket. Whenever you call a function, you always have that circular bracket. And it has there can't be any spaces. I'm pretty sure. Yeah. And COLS. It's a col. COLS means columns. Do you get what this line says? We're basically saying if we are not done, we want to set next queue to self.getQ state underscore next, or else we want to set it to np.zeros for the number of columns. If you're curious where the column calls is defined, it's at the way top of the file. You don't really need to get there. You can just hover on it. You should say like, I think 7. Yeah, literal 7, you can see that. Enter. Now you want to set the target equal to the reward. So target equals reward plus self.gamma. This is set in our class init function plus, times. Also, what we're doing right now, that's the equation. If you see line, I think 464, you can see target equals reward plus the gamma, which is that y-looking thing, times the max of q next. So we're doing times np.max, np. NP stands for NumPy. NumPy
Yeah.
is a library, yeah, max. And max is a function where we pass in q underscore next or next underscore q. Function, so circular bracket. Pass in next underscore q. Yeah, that's what we got in the line before. Next, we'll set now that queue's action. So do q square bracket. So this q is the state that was returned in 471. And we're setting this queue's action. So do action equals, plus equals, we're adding it. Self.alpha, this is defined in our init function, times. Do you see line 466? That's what we're doing right now. We're doing the queue states action. We're adding and making it equal to alpha times the target minus queue's action. So do in brackets target, minus q action. Lowercase q, right? Remember, uppercase, anything that starts with uppercase, we're assuming it's a class, which q isn't. And yeah, that's basically it. This is basically the equation written right above. We're getting the state, we're getting the state next. These are basically, we're setting up the variables. We're getting the q and the next q, which is also setting the variables. And then we're running the function, the equation. We're setting q action equals q action plus self alpha times target minus q action. Right? And you can stop sharing your screen. I don't know if you guys have any questions, let me know. James, can you share your screen? Are you able to share your screen? Or we can just continue with Blookit. Up to you. Yeah, sure. It is up to you. Then, are you guys wanting to do Blookit? We will do one for. Let me share my screen. We'll do one for Q-learning. Link is in the chat for the Q-Learning booklet. And I'll stop the recording and upload it.